Good day everyone, this is Maneth Marilia from class A13 and today we will discuss two problems about two different topics in analytical chemistry. The first problem is about introduction to spectrochemical methods and the second problem is about molecular absorption spectrometry. So these two problems came from the book of Skoog, The Fundamentals of Analytical Chemistry, 9th edition. The first problem. The complex formed between copper and 110-pentantraline has a molecular absorptivity of 7,000 liter per centimeter mole at 425-35 nanometer. The wavelength of maximum absorption. We have four questions that we need to answer here, so let's get into them one by one. We have here 7,000 liter centimeter mole, which is clearly a molar absorptivity, so let's take note of that. The first question. Calculate the absorbance of a 6.17 times 10 to the negative 5 molar solution of the complex when measured in a 1 centimeter cell at 435 nanometer. It is clear that we have a concentration here, which is 6.17 times 10 to the negative 5 molar solution. Then we have 1 centimeter here, which is clearly a path length. And we need to calculate for the absorbance of this solution. We know that the absorbance is the product of the molar absorptivity, path length, and concentration, and that came from equation 24.8, which is you can find that in page 6 on page 650 of Fundamentals of Analytical Chemistry book. So it is pretty much a direct substitution of the values to the formula. So we have 7,000 for our molar absorptivity, 1 centimeter in our path length, and 6.17 times 10 to the negative 5 molar for our concentration. Canceling units, then we will have an answer of 0.32 as 0.432 as our absorbance. Next problem. In our next problem, we need to calculate the percent transmittance of the solution in A. So that means we need the absorbance that we solved earlier to solve for this. So we have an absorbance of 0.432, and this we have a formula for that. We know that the absorbance is equals to the negative log of transmittance. That is equation 24.5, which you can find in the book of Fundamentals of Analytical Chemistry, page 658, if I'm not mistaken. So we need to isolate T. That's why T will be equal to the analog of the negative A. So it is pretty much again a direct substitution there, but we want the percent transmittance, not just the transmittance. So for us to get that, we just need to multiply that by 100%. So the A in here, we just need to transfer the value that we solved earlier. So that's A here is 0.432. Then multiply everything, and then we'll have 37% for our percent transmittance. Next problem. Calculate the concentration of a solution that in a 5 centimeter cell has the same absorbance as the solution in A. So that means we will also need the value that we solved earlier, which is the absorbance, which is 0.432. And again, take note that the molar absorptivity does not also change, which is still 7,000 liter per centimeter mole, which is pretty obvious since we only have one wavelength here. So we have here 5 centimeter as our path length, and we need to calculate for the concentration. We know earlier that the absorbance is the product of molar absorptivity, path length, and concentration. So we just need to transform this so that we can isolate C there. So we will end up with this formula. then everything is just a direct substitution of values. So A is 0.432 divided by the molar absorptivity, which is 7,000. Multiply that by our new path length, which is 5 centimeters. Then the concentration of this solution will then be 1.23 times 10 to the negative 5 mole per liter. That is our answer for letter C. For letter D, the last question in this problem, calculate the path length through a 3.13 times 10 to the negative 5 molar solution of the complex that is needed for an absorbance that is the same as the solution in A. Again, we will use the same value that we got earlier for absorbance, which is 0.432, and of course the molar absorptivity does not also change. That's why we have 7,000 for it. We have a new concentration here, which is 3.13 times 10 to the negative 5 molar. That is our new concentration, and we need to find the path length of that. So, we know that the absorbance is this equation, which is equation 24(8). And again, we will just need to transform this so that we can isolate B, which is the path length. So we will get this formula. Direct substitution of values in the formula, we will have 0.432 divided by 7,000 times the 3.13 times 10 to the negative 5 molar per liter. Mole per liter, which is the concentration. That's why we will have canceling units. That's why we will have 1.97 centimeter as our path length. And that's the end of problem number 1. Let's now move on to problem number 2. Molar absorptivity data for the cobalt and nickel complexes with 2,3-quinoxylene ethyl are 36,400 and 5,520 respectively at 510 nanometer, and 1,240 and 17,500 at 656 nanometer. A 0.425 gram sample was dissolved and diluted to 50 ml. A 25 milliliter alico was treated to eliminate interferences after addition of 2,3-quinoxylene ethyl. The volume was adjusted to 50 milliliter. This solution had an absorbance of 0.446 at 510 nanometer and 0.326 at 656 nanometer in a 1 centimeter cell. Calculate the concentration in parts per million of cobalt and nickel in this sample. So we have given of molar absorptivity for cobalt and nickel at 510 nanometer, and we have molar absorptivity again at 656 nanometer. We also have here two different absorbance of solution since we have two wavelengths. So we have 0.446 for 510 nanometer and 0.326 for 656 nanometer. We also have here 1 centimeter, which is our path length. So just to summarize the given data in our problem, I just separate the given in 510 nanometer wavelength and 656 nanometer wavelength. So this is the summarized version. We have a different molar absorptivity and absorbance between the two, but the path length does not change. It is still 1 centimeter. The first thing that we need to do is to make an equation to solve for this, for the concentration of nickel and cobalt. We know that the absorbance is the product of molar absorptivity, path length, and concentration, which is equation 24(8). That's why, but here in this problem we have two samples, which is the cobalt and nickel. That's why the sum of the absorbance of cobalt and nickel is the absorbance of the solution. We know that we also have two different wavelengths. That's why we have different wavelengths for the absorbance of cobalt and nickel at 510 nanometer and 656 nanometer. Just to simplify this equation, we know that the path length does not change. 1 centimeter is a constant here, and the concentration of cobalt and nickel does not also change even though the wavelength changes. The only thing that changes as the wavelength changes is the molar absorptivity of cobalt and nickel. That's why for the absorbance of our solution in 510, we have this equation. This will be our equation number 1. And this will be our equation number 2 for the absorbance at 656 nanometer. This will be our equation 2. We need to arrange equation number 1. Rearranging equation number 1, we want to isolate the CCO here, which is the concentration of cobalt. And for us to isolate that, we need to get that to the other side of the equal sign. That's why we will end up with this formula now. This will be our equation, the new version of our equation 1. And now recall for equation number 2. There is also a CCO here. Now let's put this rearranged version equation 1 in equation number 2. So putting that in our formula, we will now have this equation. And this one is pretty much just a direct substitution of values of the given in our problem. So I assign here different colors for you to not get confused on which is which. So this is it. And as you can see here, there is a specific variable with no color, which is the CNI. This is what we want to know. So this is what we're looking for. So solving for that, solving for the concentration of nickel, this is I just put the values in the formula earlier. So as you can see here, we need to solve for CNI, canceling units, then we will end up with this. Then further solving for it, we will end up with this. We now identify the molarity of the concentration of nickel, which is 1.8 times 8 times 10 to the negative 5 molar. But we want to know the concentration of the cobalt and nickel in the sample. That's why we will solve for the concentration of nickel in the original solution. We just need to multiply the CNI that we got earlier to the dilution factor. The dilution factor is just the final volume divided by the initial volume of the solution. So earlier we have 25 ml alcohol, right? Then we added water to that. So our diluted solution does now have 50 milliliter. So multiplying that, we know that the concentration of nickel is now 3.6 times 10 to the negative 5 molar. But the question wants us to solve for the concentration of nickel and cobalt in ppm. That's why we will convert this value to ppm. We know that ppm is the mass absolute in mg divided by the mass of sample in kg. So the value that we got earlier, we will multiply that concentration to the final volume of the solution, which is 50 ml. Then canceling units, we will have millimole there. And we need to multiply that again by the molar mass of nickel for us to get the mg of the solute, which can be identified now as 0.106 milligram nickel. Now, putting that in the formula of ppm, we divide that by the given sample. We know that we are given a 0.425 gram sample, but we want that in kg. That's why we will convert that in kg. Now canceling units, then we will have 249 ppm, and that's the concentration of nickel in ppm. Now let's solve for the concentration of cobalt in the sample. As you can see, we need to recall for the rearranged version of equation 1. This is the equation that we formalized earlier. That's why we just need to put the values in this formula. So we have 0.446 for the absorbance of the solution at 510 nanometer minus the molar absorptivity of nickel at 510, which is 5,520. Multiply that by the path length, which is 1 centimeter. Then multiply that by the concentration of nickel. Take note that this is the concentration of nickel, not in the concentration of nickel in the original sample. Okay, that's why it's 1.8 and not 3.6. So divide that by the molar absorptivity of cobalt at 510 nanometer times the path length, which is again 1 centimeter. Canceling units, then we will have this answer, which is 9.53 times 10 to the negative 6 molar. This will be the concentration of cobalt. But we want to know the concentration of cobalt in the original solution. So we need to multiply that by the dilution factor. The molarity that we got earlier, we just need to multiply that by 50 ml divided by 25 ml. Again, 50 ml is the final volume and 25 ml is the volume of the alico, and 50 ml is the volume of the diluted solution. So multiplying that and dividing by 25, we will have 1.91 times 10 to the negative 5 molar as the concentration of cobalt. But we want it to be in ppm. That's why we will convert this now to ppm. Again, we know that the ppm is mass of solute in milligrams divided by the mass of sample in kilograms. So multiplying the molarity that we got earlier, multiply that by the 50 ml for the final volume. Canceling units, we will have millimole of that, but we want the mg. That's why we will multiply that by the molar mass of cobalt, which is 58.933 milligram per millimole. Canceling millimole, we will have 0.0563 milligram cobalt as the solute. So putting that in the formula for ppm, we will now divide it by the mass of sample. We are given a 0.425 gram sample. But we need it to be in kg. That's why we will convert that into kg. So canceling values, we will now have 1.32 ppm as the concentration of the cobalt. And that's the end of learning test number 2. Thank you.